Hi, my name is Arushi Surve, and I'll be presenting hybrid nuclear solar power architectures for sustainable space habitats. So, where the research interest for me stemmed from this project is I'm an environmentalist and I'm a first year engineering student at Georgia Institute of Technology in Atlanta, Georgia for aerospace engineering. And kind of combining my two passions for space exploration and Earth and environmental sciences is where I got this idea from, looking at how we can kind of hybridize and use in situ resource utilization for space architecture habitats. So the main topic is, of course, designing hybrid solar nuclear energy systems for long-term sustainable Mars habitats. And kind of some separate goals that stem from this topic is to ensure a resilient, safe, and most importantly, a self-sufficient system for human missions to Mars and beyond. So why this matters? As we all know, Mars habitat is very resource inducing, so they need constant, reliable power for life support. And solar energy alone is inconsistent due to dust storms, day-night cycles, and weak sunlight through Mars' thin atmosphere. So combining this and coupling this with nuclear energy gives it that balance and gets the strength of both the solar energy power, which is consistent and renewable, along with nuclear energy, which has the adaptability and redundancy help. Together, they bring that more sustainable aspect. Versus relying on a single power source, which increases the chance of mission failure because both solar energy and nuclear energy have their own weaknesses. So hybrid energy is where the combination of nuclear and solar energy come from. Because, like I just said, solar energy varies with dust storms and atmospheric conditions, and nuclear power offers this constant energy that solar energy doesn't always do, but has challenges with shielding, safety, and refueling. So combining both ensures stability and continuous power, and kind of this double joint system is what I'll be focusing on in both the presentation and my research work. So the concept of both is the solar power will be used when sunlight is strong to power habitats and charge storage systems, while nuclear power will be used when sunlight is weak to maintain critical systems. So only nuclear power will be used as kind of a generator. And the energy synergy comes from excess solar energy that can heat and neutralize water to be stored, while nuclear energy stabilizes output during solar fluctuations. And so this kind of closed loop cycle improves efficiency and resource use within the Mars habitat itself. So this is the study design, and it will compare kind of three configurations. The first will be the solar dominant one, second will be nuclear dominant one, and third will be a true hybrid one, where, as I just said, that in case of dust storms, not having access to solar power, nuclear power systems will be into play. So the evaluation criteria for my study design will be energy density, mass to volume ratio, installation complexity, maintenance frequency, and fuel requirements for desired outputs. So the models will be tested for Mars, and then normalized to also apply to other extreme environments. So the broader implications of my project are mainly that this insight that I learned from hybrid nuclear systems can apply to clean energy transition here on Earth as we are shifting from wind, thermal, solar power. It provides a way to kind of test hybrid systems in an extreme environment such as space. It also supports sustainable power in extreme environments on Earth where there's disasters, there are remote environments, or resource scarce areas. And it also establishes a pathway toward permanent Mars settlement. So this is kind of sums up the slide of the previous work done on whether that's reactors or energy poweration. I'm not going to go too into it because I could talk about this for a very long time. But it is here as reference. These are some of the articles that I referenced while coming up with the idea for this project, as well as the method. and identifying the gap of research. So, to sum kind of this section up, hybrid architectures have been studied conceptually and with system analysis, and researchers have proposed hybrid architectures with solar and fission before. And NASA has also developed and tested small fission reactors. Solar hybrid subsystems are an active topic in especially European agency research. The fourth point is that location matters. Solar often is used a lot at Martian sites when mass and storage strategies are optimized, just because it's a renewable source that's easily accessible on Mars habitats. But nuclear also offers that on demand and resilient technology that is really needed in order to ensure the success of the mission. And then the last one is that systems level NASA plans and integrated surface power studies explicitly considered these mixed or distributed approaches as I'm doing in my research. So the findings focused for this research will be resilience through redundancy, looking at where energy powers are not redundant but can still remain resilient so that critical systems especially can still continue to go on in the event of disasters, dust storms, any kind of unpredicted extreme environment weather. The second is that trade space is sensitive to mass efficiency and local illumination. So I'll be looking at where nuclear becomes more favorable for high continuous load missions. The third is that thermal management and shielding are important for fission options. So looking at shielding mass, thermal rejection, and reactor geometry to make sure that the crew is not exposed to dangerous nuclear power. And the fourth one is power management for hybrid systems, looking at how variable inputs and outputs of energy can be combined to deliver steady kilopower, looking at scheduling needs, advanced conditioning, control logic, and kind of making sure there's that mechanism that switches from solar to nuclear efficiently and almost immediately in the case that steady solar power is not available. So yeah, that's it for kind of the brief introduction and segue of my research. Thank you so much for having me again. I've included my email, my LinkedIn um, for you to reference. And if there's any questions now, I'd love to take them.